And as I emphasized last time, a Hilbert space is a special case of a Banach space. So recall that a Hilbert space is a vector space H equipped with we take a complex vector space. There are also real Hilbert spaces, but we look always at complex Hilbert spaces, equipped with a then sesquilinear inner product which induces a norm. With respect to which H is complete. So we're guaranteed that every Cauchy sequence converges. It's very easy to observe, well, I already said it, because you have this norm defined on a Hilbert space, namely by virtue of the norm of psi. So we'll usually denote the elements of a Hilbert space by some psi, phi, tralala, because this is defined like this, and this is indeed a norm, makes this into a Banach space in particular. If you take this norm, makes the Hilbert space into a Banach space. And thus we know from our work we did on Banach spaces, we know that everything we know about Banach spaces already applies. For instance, we know that if we look at the set of bounded linear maps from the Hilbert space into itself, and usually last lecture we had here Banach spaces, but the Hilbert space is in particular a Banach space. We know that this space equipped with the operator norm. So let me maybe indicate this norm by an H just for a while, because it's the norm on the space H. And here we have the operator norm that we defined last time. That's a different norm than this one. It's the one that's defined on this space. Okay? We know that this is a Banach space. Okay? So you see, even if we start with Hilbert spaces as a special case, you could say, why would we ever look at Banach spaces? Well, already the construction of the set of all bounded linear maps from H into itself carries a norm is a Banach space, but not a Hilbert space. However, there is a special type of Hilbert space, and that because H is a Banach space, I know what H star is. Do you remember what H star was? So this is point A, point B. H star was what?
The dual space.
Yes, the dual space, but how is it defined?
As all linear maps from H to the real numbers or complex numbers.
To complex numbers? No, not quite. Not all linear maps.
All bounded.
All bounded linear maps. Please don't forget this. This is all bounded linear maps from H to C. So you quoted the linear algebra notion. If you don't have an inner product, if you don't have a norm, then you can't talk about boundedness or not. But if you do, we explicitly restrict to bounded functionals. Bounded functions are also continuous. That comes on the problem sheet. We know that this space here, equipped with the corresponding operator norm, which it is also a Banach space, because it's just a special case of this situation if I had a different Hilbert space G here, because the C is also a Hilbert space. Okay, so you already learned that. Remark, we will see that the dual H with the norm it carries is even a Hilbert space. And somebody already said it last time, that can only be, so that means that there exists an inner product on this H star such that the norm on H star, which we already have by virtue of the construction of the operator norm, such that this norm is given by an inner product, by the square root of an inner product. Okay? We will see. Okay. So, but that prompts the more general question. So, in order to see this, so you see, we're abstractly guaranteed it's a Banach space, but the question is it even a Hilbert space? In order to see this more generally, note the theorem. The theorem is the following. If a norm on a vector space is induced by a sesquilinear inner product, if and only if. And if I say induced, I could mean many, many things, but I really mean induced like this, okay? You could induce it maybe otherwise. If and only if the parallelogram identity norm of f plus g plus the norm of f minus g equals twice the norm of f plus twice the norm of g holds. And of course for all f and g in the vector space. So if this parallelogram identity holds, then the norm really comes from an inner product. In this case, when it does come from an inner product, the inner product can be explicitly constructed up here, constructed as, well, you want to learn how an f with a g, what the inner product is. Because we have a sesquilinear map, it works as follows. It's 1/4 bracket. You take f plus g norm minus f minus g norm. So the plus goes with the plus and the minus goes with the minus. Then you take plus I times f minus I g minus I times f plus I g. Close bracket. So you see the minus I goes with the plus I and the plus I goes with the minus I. On the right hand side you only use the norm, but what you get is the inner product. This is called a polarization identity or polarization formula. But mind you, if you didn't check that the norm satisfies the parallelogram identity, you can write this down, but the resulting object will not have the properties of an inner product. So you need to check this first before this is true, before this yields an inner product. And then that is the inner product that induces that norm. Okay? So the proof of this is on the problem sheet. Okay? And the proof that H star, the dual of H, is even a Hilbert space is afforded exactly like this. And it's also on the problem sheet. Okay, so because we invested some work with the Banach space, we don't have much work to do here. Okay? And actually the whole, this should all be the first section called relation between Hilbert and Banach spaces. So first section, relation between Hilbert and Banach spaces, if you want to write that down. Okay, so there is an important estimate on Hilbert spaces. And that comes in the form of the theorem that f, oh, well, let's take psi and phi. Psi and phi, absolute value of the inner product, is always less or equal than the norm of psi times the norm of phi. So you see, I now don't write sub h because it's obvious. So increasingly, I will not mention explicitly on what space the norm acts, because you see on what space it acts. So you have to see, is this the norm on the Hilbert space? Is it the norm on the dual space? Is it the norm on, is it the operator norm on some more general L space, and so on? Okay, so this is the Cauchy-Schwarz inequality. Cauchy-Schwarz inequality. Okay? Okay, and the proof is simple, so homework. All right, so this will often be used. You saw already last time we used one or the other inequality. If we want to show something is Cauchy, something converges, and so on, you know that in analysis, making these estimates in proofs and in calculations, that's part of the art of analysis, right? In algebra, you always have equal signs. That's very simple. Estimates are more of an art because you have to see, okay, right? There are many estimates you can make, but there are rarely many equations you can write down. Okay, so anyway, this is a very, very useful estimate. Right. So are there any questions so far? I think most of this you must have seen before. It's only good to know that also in the infinite dimensional case with our inner product and the norm, we have, for instance, very clear about the dual spaces, namely only the bounded linear functionals. It's very important. So normally, you know that choosing a basis on a vector space is something that's a little bit, well, vulgar. Most statements are made beautifully without bases, and they're actually much clearer without having chosen a basis. However, sometimes you want to have a basis, and in contrast to what I just said, some theorems and some statements are most easily written down using a basis. And if you really want to write down a specific map or a specific vector rather than an arbitrary vector, you usually employ a basis and then you provide the components of that vector, if you will. So we need to look at the concept of basis. And now you might think you already know this because a Hilbert space is a vector space in particular. So you say, well, we know what the basis of a vector space is. We even know what the basis of a vector space is if the vector space is infinite dimensional. Yes, I believe you that. The point is, those are not the bases the quantum mechanics textbooks talk about. Nevertheless, let's review the standard notion of basis, and then let's talk about the other one. So this section is called Hamel versus Schauder. So what sounds like a boxing competition is in fact two different notions of basis. And I claim what you learned in your linear algebra lecture is the Hamel basis, and you just called it basis. Okay, the notion of basis for a naked vector space V plus S multiplication. By naked, I mean it has not more structure than a vector space. It does not carry a norm. It does not carry an inner product, let alone such that it's complete. You just have a naked vector space. Is known from linear algebra, which is the theory of vector spaces, first and foremost, without any additional structure. And it's the following, and it's very useful to write it down again to really contrast this. Definition: a subset B, or B in the vector space is called a basis, or let's write a Hamel basis. But again, if you don't say Hamel, you probably say what is the right answer in the linear algebra examination. It's called a Hamel basis if, well, the first thing is if any finite, and that's the key word, if any finite, even if the vector space is infinite dimensional, well, we don't know what dimension is yet before we have a basis, okay? But if any finite subset, so we can give it a name, E1 to En. If it's finite, it goes up to some n. If any finite subset E1 to En in this basis set is linearly independent. And let me write down once more what that means. That means if you have the sum I equals 1 to n, so if this happen to be n vectors, and you look at lambda I ei, so these are vectors and these lambdas are complex numbers, that already implies that the lambda 1, the lambda 2, up to the lambda n are all 0, where these are all complex numbers, right? You know this definition. But if the basis has not finitely many, we're not requiring that you take all the elements of a basis and go up to infinity, but you require that any finite subset has this property. Then the B is called linearly independent. A subset may be not finite. It's called linearly independent if any finite subset of it is linearly independent. And the second condition is called the basis. So it's the linear independence. Now we come to the generating property. If for any V vector in the vector space, there exists, and now it kind of comes, it exists a finite, there's again this finite thing, there exists a finite subset, let's call it again E1 to En, but you see, this n is not fixed, it depends on the V, subset of B, and corresponding, well, and complex numbers, we're dealing with complex vector spaces, and complex numbers V up 1 to V up n, as many as you have elements in here, such that the V can be written as a linear combination I equals 1 to this n Vi Ei. And if they're linearly independent, it's also unique. I don't need to require that they can be uniquely written like this, because that follows from number 1. That's it, and that's how you use bases, okay, in general. And then you have definitions or terminology. Well, and you can show, okay, there's lots to be said, but terminology is if there exists a finite basis, B, then the dimension of the vector space is defined as the size of the set B. Okay? Else it's called otherwise dim of the vector space is said to be infinity. Okay, now of course one has to show well definition of these numbers. It could be that another basis has another number of elements, or is not isomorphic to the other bases as a set, but that can all be shown. So this is what you know, and however, that's the important remark, this is not the notion of basis that quantum mechanics books, textbooks, wish to talk about. And it's a very important point, because an amusing homework could be to go to the library and follow all quantum theory books that make that clear. So you just talk about basis, but it's not quite that innocent. For in fact, on a Hilbert space, and you could probably also do this on a Banach space, but let's specialize to Hilbert space. For in fact, on a Hilbert space, H plus times, which is not quite as naked because it's clothed in a charming inner product, one may define another notion, or a modified, a refined, that sounds good, a refined notion of basis. And that's the definition I'm going to write down now, and that's the definition we're going to use. Definition: a subset S, now we call it S, a subset S of a Hilbert space is called a basis. But not just any basis, it's called a basis, and to distinguish it from that basis, we call it a Schauder basis. It's called a Schauder basis, and so you see, from now on we'll only talk about Schauder bases. So if in the future I don't say Schauder before it, you should always mentally insert it, okay? And whenever you think about naked vector spaces, you should mentally insert Hamel basis. A subset is called a Schauder basis if, well, the first condition is unaltered. The first condition is like for a Hamel basis. Okay? So for, well, same as for Hamel basis, only that now B is replaced by the S. Okay? So require that any finite subset of this set be linearly independent. Nothing new. Well, it's in the number 2 where the difference comes up. Second, for any psi in the Hilbert space, psi instead of the V, there exists, and now comes the big difference. Here we said finite. We still have finite in 1. But instead of finite here, there exists a countable subset. You know what a countable subset is? That's one where each element can get a number. It's a sequence, right? A sequence of elements. There exists a countable subset, E1, E2, dot, 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 and it doesn't end. Or maybe it does end, then it's finite. Finite is part of countable, but it could be infinite, but countably so. You can give labels, 1, 2, 3, and so on. If there exists a countable subset in this basis set S, and a sequence, could have also said a sequence of vectors, right? It's the same thing. And a sequence psi I, well, I is the label of the sequence, psi I in n. Well, I should say I in 1, 2, da, 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 da. If this terminates at some d, then this terminates at some d. If it doesn't, it's say in a sequence of complex numbers such that psi equals, and now we have two cases, psi could equal sum I equals 1 to sum d, psi I ei, and this is the case if if the basis here, if the basis set S has finite size, or if that's not the case, then it goes up to infinity, psi I ei, else. So this is the generic case, okay? So now you say, okay, why didn't we define this like that in linear algebra? Any ideas? Yes, of course you do. In linear algebra, you do deal with the infinite dimensional vector spaces. If you take the definition of a vector space as a set V with operations plus and S multiplication, and you have Kani and Adu as your axioms, it says nothing about dimension. Maybe a specific linear algebra course deals only with, that's true, but linear algebra deals with infinite dimensional vector spaces as well. No, that's not the reason. What of all I wrote down here can you not do if you don't have an inner product on your space or a norm? Then you have no topology, and if you don't have topology, what don't you have? What notion depends on topology that you might need here? That's right. Continuity you don't need immediately. Well, you need convergence. What is supposed to converge here? Aha. It's a series. It's a series. And series are serious. So the thing is, I mean, you don't know what this symbol means. You can write infinity, but what number do you assign to this? So recall, if you write something like this, that the sum of n equals 1 to infinity over some sequence of whatever, here it's a sequence of vectors, because this is a vector, there's an element in H for each I. This is defined as the limit, capital N goes to infinity, of the partial sums, where you go only to a certain member here, but then you have to take the limit. Now, this here, each of these is an element in H. Do you agree? Because finite sums in a vector space, you can add 2 together. You can add 3 together. But if you know how to add 2, you know how to add a finite number by induction. But by induction, you do not know how to add an infinite number. Maybe I should set up a warning sign. So one warning sign is that if you have a linear map A, okay, and you let it act on an infinite sum, psi I ei, right, with our notation, you cannot, by linearity, conclude that you can pull the sum out. Right? You cannot, because linearity is defined for A of psi plus phi is A of psi plus A of phi. It's defined for 2. Hence, it's defined for a finite number n of summons. But it is decidedly not defined for an arbitrary number. Well, if you know that this means a limit, and if you know that the A is continuous, a continuous linear map, then you can pull first the limit out, then you have a finite number in there, namely the partial sums, and then you can pull the partial sums out. So this is not true for any linear map, but for any continuous linear map. Do you get a feel why we want H star to be the bounded functionals from H to C? Well, because bounded also means linear, it's on the problem sheet. There you can then do it. Continuous. Bounded means continuous, yes. right? And then you can do that, because then you can pull the limit out. Huh? So we're not going to be careless about this, because this is very, very important. Okay, so here you need a notion of convergence and on H. So this requires a notion of convergence on H. Well, if you made your vector space into a topological vector space, you gave it a topology, well, then all is fine. So some people might say, yeah, but every vector space is some r to the n. Yeah, every finite dimensional one, but there you don't have a problem in the first place. Okay. Anyway, so you need a notion of convergence on H, which is precisely where the inner product comes in. So in a sense, at this point here, the inner product is needed. And hence, this is not possible in linear algebra for a naked vector space. It's only possible on a Hilbert space. It's a very subtle, a very small thing that you very easily don't look at. And the bases in quantum mechanics are like this. Now, let me ask you, you could, of course, say, all right, I have a Hilbert space and I have an inner product. I could forget the inner product and provide a Hamel basis for this Hilbert space, because, I mean, nobody forces me to use the inner product. I have a perfect notion of basis for a Hilbert space that does not employ the inner product, and that's the Hamel basis. So you could say, okay, why don't we choose the basis we already knew? Why do we need to invent a new type of basis? Well, the point is you don't need to invent it, but it's convenient for the following reason. Imagine, roughly speaking, I take one and the same Hilbert space, a very specific one. Which basis set is usually larger for the same Hilbert space? If I ignore the inner product and I provide a Hamel basis, B? Or, alternatively, if I use the inner product like this and I provide a Schauder basis S? Which set includes which? So the question is, what is true? Is B usually smaller than S, or is S, or smaller, contained in B? Well, very roughly speaking, it's a very, in quotation marks, right?
The first statement is obviously true, since countable includes finite.
No, it's not. It's obviously wrong.
Because the inner product provides extra structure. Oh
Yeah.
In the basis.
Yeah. Okay, no, but one can. Okay.
And you have a problem with the finite one.
No, forget the final one. Say it's an infinite dimensional vector. Well, okay.
Timo made the right argument,
Yes.
but he said it the wrong way around. I mean, countable includes finite, so the below statement.
No, but look. This set. Hang on a second. So this set B, nothing is required of the set B. Here, nothing is required of the set S. I mean, as far as its finiteness, countability, or anything is concerned. This B, so far, later on we'll specify to separable Hilbert, but so far this B could even be over-countably infinite, non-countably. Pardon?
If you want to generate a vector.
If you want to generate a vector, what happens? Right. Here, you can reach a vector possibly by taking the guys from S, but infinitely many of them, and taking a limit. Whereas in the Hamel basis, you need to reach the vector by writing down a finite combination. So for instance, assume you have consider a Schauder basis and assume a certain vector is such that you do not reach it by a finite number of summons, but only by an infinite one. Well, if that is true, then the Hamel basis needs to provide that limit as an extra vector in here, because you would then have to reach it directly rather than getting it, okay? So in general, the Hamel basis must be much bigger, because in the Schauder you can afford to choose fewer, because some you hit by adding infinitely many. Is that clear? You have more power in generating vectors. You can generate vectors in a more powerful way here than there, and hence you need less to generate it from. So the American argument is if you're an ingenious guy, from very little you make a lot. Okay, so that's the Schauder basis. Okay, because you have many means of operating. The Hamel basis is a poor basis. No, it's not a poor basis. It's someone who's not very clever in using his or her resources. You can only act with the resources in this way that you add finitely many. Okay, the motivation for choosing the Schauder basis is A, we can because we have sufficient structure, and B, it makes the basis smaller in this sense, okay? For a finite dimensional space, there's no difference. The concepts coincide, obviously. But for infinite dimensional Hilbert space, this is very important. Okay, so I'll formulate this as a remark. Remark, since using the notion of a Schauder basis, one has a more powerful means of generating a vector in a Hilbert space. One needs less resources, that is, roughly speaking, elements in S than one needs in a Hamel basis B. Less or equal, right? Of course. Anyway, Schauder bases are the bases that quantum mechanics textbooks talk about. And you will find always these sums over vectors and so on. Well, in some you find even integrals over vectors. Well, that's a different business that goes again in the direction of being a little bit sloppy. I will do this more precisely. Anyway, so this is a basis. Yet another remark. Schauder condition 2, where we say you can generate like this, can be rephrased as follows. And I rephrase it not for rephrasing's sake, but because an important notion appears. You can split it into 2.a. First part is you define the span of a set of vectors. Define the span. Define the span of a set of vectors, and the set could be a set M, where M is some set of vectors. And do you see, I assume nothing on M. It could be even non-countable. Okay? An arbitrary subset. What is the span of an arbitrary subset of vectors? The span of M, we agree, is the collection of all finite linear combinations of elements of M. So if you want to look at the span, you know what the span of three vectors is. It's a linear combination. Any linear combination of the three vectors is the span of the three vectors. The span of countably many vectors could give you countably many vectors and ask you to write down the span. Well, the span does not consist in the infinite sums you could build then. It only consists in all the finite sums you could build. And if in the future we talk about the span, we will always use this definition for very good reasons. And then 2b, so this has nothing to do with this apparently, because here we do exactly the opposite. We can also take the limits. And 2b is then the statement that the span of the Schauder basis is dense in H. Or in other words, that if you take the span of the basis, which is how you usually think. You think if you have a basis, you take the span of the basis and then you have the entire space. But because the span only takes the finite ones, this would be a Hamel basis if I now required that the span of S be H. If I require this, then I get the Hamel basis, because then I must reconstruct every vector by a finite linear combination. Is that clear that that would be the Hamel basis? So forget the dense thing. But the requirement here is that this be dense in here, but it doesn't need to be this thing. It could be a subset, but a dense subset. So if you take the topological closure of it, it coincides. So this is the topological closure. Okay? So look that up if you don't know that notion. It's logical closure. So hence, if we were dealing with Hamel bases, we would never see these closure symbols coming up, these topological closure symbols. And we deal with Schauder bases, and you think, oh, so it's not the span of the basis, it's the whole space, but only the closure of the span. What is this about? Well, it's exactly this. The span is the finite linear combinations, and you want to admit that you hit an element not by a finite one, but by the limit of a sequence. Hence, you require this. So this looks more complicated at this level, but it actually makes the whole thing simpler because the Schauder basis needs fewer elements. Well, fewer, you know, in the set sense, inclusion sense, and whatnot. Okay? So this condition here demystified. And sometimes the second condition is just said, so the subset is called a Schauder basis if any finite subset is linearly independent. Second, if the span of S topologically closed is the Hilbert space. And I tried to go step by step to give you a more elementary feeling for what that means. It all means the same, okay? It's actually very simple. So don't lose your fear of this guy. It means you complete this. You don't only take the finite ones, you take sequences and their limits, and that's this. So there's one final point that Dominic convinced me of here. There is something incomplete about my definition of Schauder basis. And Dominic's question was, hang on, all is fair enough, but why wouldn't you simply, if you have a certain Schauder basis S, why wouldn't you simply take a Schauder basis S prime, which contains all the elements in S from which these EIs are taken, and you add as an extra vector some infinite linear combination, which therefore is a new vector in S? Well, you say, well, because then you have two ways of representing a vector, this vector psi. You could say it's simply 1 times this new element in the basis. Or you could say it's this series of the other elements in the basis, or some other elements in the basis. So you no longer would have uniqueness of coefficients, of uniqueness of expansion. And my immediate answer, which I now increasingly believe is not correct, is, well, you go to the linear independence bit and you see that that can't be true. But then Dominic's counter-argument was, hang on, you say the linear independence is still defined looking at only finite subsets of the S and then of the S prime. So you could not compare with the series with the other one and see that one is linearly dependent of the other. I believe that that is a correct objection. And to be sure, I would like to add, just to be safe, a third axiom. And next time I maybe show you the theorem why the third axiom is redundant. No, I don't think so. I think it's correct. So the third one should be, S is called a Schauder basis if all of this is true and if S is a proper subset of some S prime. Let me think. If S was a proper subset of some S prime, no, I want to say something like S is the smallest such, the smallest such set. So S is the smallest such set, okay, that is, it's not so easy. It's not so easy to formulate it because you could choose an entirely different basis, which is not even a subset, but is. Let me leave it here. So I do not allow you to add another vector like this. Okay, and it shouldn't have been added before. S is the smallest such set.
Smallest subset with respect to inclusion, maybe.
Yes, that's right. Yeah, in principle that's right. But see, you could choose an entirely different basis from the start, and then one is not included in the other. So another basis, another Schauder basis, wouldn't necessarily be a superset.
Yeah, but then this is another completely different
That's right.
basis that is then isomorphic to the other basis or the other smallest basis.
Yeah, something like this. Something like this.
Is that exactly what you prove in linear algebra with the Thor lemma, actually? By proving that the basis is a small subset, as a largest subset with the linear independence? The Zorn lemma comes also in at some point because this S might be non-countable. Yeah, exactly.
Let me leave it here like this, because we're now going to specialize to separable Hilbert spaces, where the S is required to be countable. And that, I think that in the end lets you deal without Zorn's lemma in this case. Okay? I mean, it's getting a little deep here for me. Let me leave it like this as a safety net, okay? And next time I'll tell you more about it. Okay? But I also think there is something to be said at this point. I now agree this is likely. Okay? Good. Okay. So now next section is separable Hilbert spaces. In quantum mechanics, proper, what do you mean by quantum mechanics proper? I mean, in contrast to quantum field theory, we always only look at separable Hilbert spaces. At separable Hilbert spaces. So what is that? Definition. A Hilbert space is separable if it has a basis, a Schauder basis, but if I had omitted it, you would have inserted it. If it has a Schauder basis S, which is A countable. So now in this definition here, we had countability, but it was a countable subset of the S and a countable number of complex numbers. Now we talk about the countability of S itself. Okay? If the S is already countable, which is countable, and which is B, orthonormal. What does that mean to be orthonormal? That is, for any two E1, E2, okay, that is for any E1 and E2 in S. It is true that the inner product of E1 and E2 is either 1, that's the normal bit, is either 1, but that's only the case if E1 is already equal to E2, or it's 0 otherwise. That's an orthonormal basis. That's the ortho. So the first one is the normal, and that's the normal, and that's the ortho. And it's for any pair, right? It's for any pair of vectors that this should hold. Now it's common notation to write EI, EJ equals delta IJ, where the delta IJ is exactly that. I1 if I equals J, and 0 if I doesn't equal J. This is, of course, all right, because the symbol delta with two indices down can be defined like this. But it is not. This delta with two indices down are not the components of the identity map on H with respect to this basis. You know, if you have a linear map, we're going to do this, so I put it on the problem sheet. If you have a linear map and you have a basis, you can express the linear map, at least for bounded operators. You can express it in terms of matrix components, right? The identity would need components one index up, one index down. If you remember the classical mechanics course, right? It's an endomorphism, blah, 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 blah. Well, depending on notation, this one here is a bilinear form. There's something, bilinear map, something entirely different from an endomorphism. Okay, so hence, a delta, the Kronecker delta. Well, the Kronecker delta. There is no the Kronecker delta, and this has a lot to do with this base. Anyway, so I just mentioned this, and of course I will also use the symbol because it's very, very useful. But really, delta up down is something entirely different from delta down down. Take it really as a symbol. People call it the Kronecker symbol, and as a symbol, it's really good because it just means this and this is right. Okay, but don't draw further conclusions from it. If you didn't understand the remarks, don't worry. Well, everybody has his own idiosyncrasies, and mine is if the indices are placed wrong. So it's my relativist training that makes me shiver when I see that. And of course, it may lead to problems at some points, and it's almost undetectable if you are not aware of the problem. You commit terrible mistakes, and you can prove fantastic theorems thereby. So anyway. So this is this. Now, yes?
I can't read the last two words.
That's intentional. So the delta ij are not the components of the id down H identity map on H. The map that sends an element of H to itself. Psi is being sent to psi by the identity map, are not the components of the id down H with respect to this basis. It's like when your grandfather starts talking about the war and he goes on and on and on and on, and you just ignore it, okay? So or great-grandfather, I don't know. You need to make an adaptation to the generation. I don't know. So now we look at separable Hilbert spaces, and I said in quantum mechanics proper, so that's the course here. Actually, I think now that I wrote this down, I probably forgot the word separable in the axioms, did I? When I said in to every quantum mechanical system there corresponds a Hilbert space. Did I say separable? No, please insert that in the axiom, because the axiom should already say that, separable. Okay, we look at separable Hilbert spaces. It doesn't look to be such a fantastic restriction. Okay, the basis can be uncountable, is countable only, and so on. The existence of a normal basis. Remarkably, there is only one separable Hilbert space at all. Well, if it's infinite dimensional, right? So we only look at the infinite dimensional case, because for the finite dimensional case, it's clear anyway. The finite dimensional complex vector spaces are the C to the n's, right? And every complex vector space that's finite dimensional is isomorphic, unitarily isomorphic, we'll talk about this in a second, to C to the n. But now you say, yeah, okay. You know this theorem for real vector spaces? Every finite dimensional real vector space is isomorphic by linear maps, bijective, and so on, to R to the n. And that's the justification for people to write down matrices all the time and components of vectors and so on, right? And for infinite dimensional vector space, it's somewhat different. But now we look at not at infinite dimensional vector spaces, but at Hilbert spaces in particular, and even more particularly at separable Hilbert spaces. How many are there? And the answer is there's only one up to isomorphism. And the axiom in quantum mechanics says, every quantum system underlies tra-la-la-la, so we have to show a theorem. Well, the claim is, and we need two more little sections to show that this is true. The claim is any infinite dimensional separable complex Hilbert space, let's give it a name, H plus times is, and now comes a word you don't know yet, is unitarily isomorphic. And sometimes people call this unitarily equivalent. It's unitarily isomorphic to the separable, that's just the claim at this point, Hilbert space of, well, that has a name, it's called L2 of the natural numbers, L2, the space tralala of all square summable sequences, complex sequences in C. So what is this space? So the space is called L2. The set is called L2 of n. This contains all the sequences A. What's the sequence? A map from the integers, from the natural numbers into the complex numbers, and the condition is it's square summable. So if you take the infinite sum, so I don't know, what is n? N includes the 0 or not? Nobody knows. N star does not include the 0, therefore I start at 1. What's the Dean norm?
Actually, it does not include the 0.
This one?
The n, the normal n.
And this one does?
No.
Well, you should study the German industry norm on mathematics symbols.
But due to the definition, you start your first element.
Which definition? Whose definition? Well, the point is that, okay, so if you want to be precise, if you want the 0, you write the 0 here. But I think there is a German industry norm. So, so international listeners to the video may laugh. So there is an industry norm, and I think that there's an official definition, almost state definition of. Anyway, so I mean it without the 0, obviously. Okay, so it's the absolute, it's the AI absolute value squared. This thing must be finite. Those are called square summable sequences, and we also need an inner product on it. Well, this is a set, okay? This is a set. Now, what do we need to make it into a Hilbert space? Well, we need an addition. How would we define the sum of two sequences? Well, pointwise again, right? And the S multiplication too. So that's again the pointwise strategy to define, to inherit the addition and the multiplication from here onto here for a sum, for an addition, an S multiplication. Okay, plus times pointwise. And that leads to an L2 of n with this plus and this S multiplication being a vector space. Well, you need to check Kani and Adu.
But why do you define the multiplication pointwise?
The S multiplication.
Okay.
So this goes from L2 cross L2 to L2, and this goes from C cross L2 to L2.
Oh, okay, yeah.
Aha. Yeah, okay, right. And so what you need then, so then you make it into a vector space, and then moreover, what we of course need, you also need an inner product on this L2, and you need to define it. And it's defined as I equals 1 to n. You take the ith member of A, you take the complex conjugate of it, you take the ith member of B, and the claim is this is a sesquilinear product on L2. You can check that. And the even bigger claim is L2 of n with this plus and this S multiplication and this sesquilinear inner product is complete. Hence Hilbert. And claim it's separable. Okay, so I wrote down a very concrete and in fact rather simple, right? I mean, this is technically very simple, it's just sequences. A very simple space which I claim is a separable complex Hilbert space called L2 of n. So that's the claim in the claim, but the point is I say any infinite dimensional separable complex Hilbert space is unitarily isomorphic. That's the key word. To this guy. What does that mean?
N has to be an infinity, doesn't it?
Thank you. Yes. What is this unitarity condition or unitary equivalence? What is it, and in particular, why would we ever look at it? So that leads to the next section, 4, unitary maps. Unitary maps are of the utmost importance in quantum mechanics, and one might think that this is a statement about nature. But in fact it isn't. It's a statement, it's simply an outflow of the structure we have. Because quite generally, one is interested, for good reasons, interested for obvious reasons even, in the structure preserving maps between any two spaces of the same type. Okay, quite generally, what I mean by this is the following. So let's look at a collection of spaces. Let's look at what the structure on this space is. Let's look at what the structure preserving maps would be. Preserving maps. And then let's look at the terminology. So this is something that is worth thinking about once, and then you're never confused ever again in the future. So the simplest set of space, I mean, space is a general notion. A specific mathematical object would be a set M. What's the structure of a set M? Well, the only structure you have roughly speaking a measure of its size. So this goes to set theory, you know, cardinality and Cantor and blub, 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 right? What is to be known about sets? About a set, all you can really know is its size. There's no further structure. And the structure preserving maps, which in fact define the size, are the bijections. The bijections that take a set into another set in such a way that it's 1 to 1 and on 2. So there is a pairing of elements by such a guy. If there exists such a bijective map between two sets, then the sets are said to be of the same size. Hence, size is preserved by these guys, and we call these isomorphisms, such maps. Bijections are the isomorphisms, and sometimes one adds are the set isomorphisms. Iso means the same, and morph means form. An isomorphism is something that has the same form. Well, because to a set belongs its structure. Well, you can become a little bit more general and to stay within the levels of structure we had in this course. You could, for instance, also equip the set with 2 more structures and you make it into a vector space. Of course, you could also have a group and other stuff, right? So there's stuff in between, but that's not the point. My point is that in a vector space, you have new structures. You have an addition and you have an S multiplication. Let's say it's a complex vector space like we have it. Now, in particular, a vector space is a set, but a vector space is more. So if you now want to look at the structure preserving maps of this structure, you certainly need to take the conditions you had for the weaker notion, for the more general notion. So certainly structure preserving maps are still bijections, but you need bijections that also preserve these structures. So if you go from one vector space M into another vector space N by some phi, and these are vector spaces, you want to preserve the plus on M and the plus on N and so on, in the sense that you could, for instance, add 2 vectors here on M and map the result, or you map the individual vectors and you add the results, and then that plus is a plus on N. And so this is, of course, what we usually call the additivity condition of a linear map. And here you could have lambda times M equals lambda phi of M, and this S multiplication here is the S multiplication on M, but this S multiplication here is the S multiplication on N. So you see, the structure preserving maps on a vector space naturally are the linear maps. That is why linear algebra is full of linear maps, because linear algebra is the study of vector spaces, and you look at the structure preserving maps. So this also has a trivial name. Sometimes people call this vector space hyphen isomorphisms. because they do exactly this. Now, I could continue with this and could put the norm and whatnot. Let's take the Hilbert space, because that's our case. And I think this triple of examples makes my point already pretty clear, I hope. Now let's add yet another structure. Let's add an inner product, a sesquilinear inner product. So you, of course, still have the set structure. Of course, you still have this structure. I don't even need to repeat this. What you have additionally here is the inner product. That takes you from m cross m into the complex numbers in a certain way. What are the structure-preserving maps? Well, certainly it's still the bijections. Certainly it's still the linear bijections, because that you inherit from Hilbert space being a vector space in particular. But there is one more structure that you would like to talk about, a preservation of it. And what you do, you say, the additional condition is now that if you take an inner product and you mapped the vectors in there, let's call them M1 and M2, you first map the vectors by your map, and then you take the inner product. That should be the same as taking the inner product like this, because the result is in C, so I can't apply the map phi there again. So it doesn't matter of whether you moved all the elements in the space, the inner product is not affected by that. Okay? Linear, and now there is an additional thing we want to have. We want it to be bounded. We want this to be a bounded linear map. Okay? And that is for certain reasons. But you see, the logic is pretty clear. The more structure you have, you always want to understand what preserves the structure. And then it's clear, I mean, as a physicist, you immediately believe that. If I say, I describe something like in this coordinate system, say, or in that coordinate system, you say, well, you can do what you like. It doesn't change the physics. Okay? And so this is exactly what these unitaries do. So if quantum mechanics is based on this structure, and I can apply a map with this property, and the structure as such is preserved, then this is just bookkeeping, which vector I call which and so on, roughly speaking, okay? We will never be interested in any statement beyond unitary equivalence, right? Okay, yeah, you can map this all to another, apparently to another space, but if this is a bijection, all the structure is preserved through the glasses of Hilbert spaces. There is no difference. If I look at a Hilbert space through the glasses of set theory, I don't see all this structure. I only see the set. If I look at the Hilbert space through the glasses of vector space theory, I see all of this, but not the inner product. And if I put on the sharpest glasses I have for a particular structure at hand, then I look at the isomorphism with respect to that. And here it's tradition to call the Hilbert space isomorphisms, to call them unitary maps. But this is just terminology. What are the isomorphisms of topology? Bijection and continuous in both directions, right? Because continuity pre-image of open sets are open sets. It preserves the open sets, right? What are they called? Topological isomorphisms. One calls homeo. In German, homeo. In English, homeo. Homeomorphisms, and so on. So there is kind of some traditional nomenclature in that, okay? But the logic is crystal clear. One could call all of them isomorphisms and always say for what structure. So, in order to not have this definition squeezed somewhere there, I write it down more clearly, because this is a central definition for the whole subject, obviously. So a mathematician who would have, an experienced pure mathematician who would have seen our first axiom of quantum mechanics, he would have immediately said, oh, unitary maps must play an important role in the theory, because you always want to classify up to unitary equivalence, because that doesn't make a difference through the glasses of the theory, does it? You see, so a mathematician would have immediately captured that. Well, now you got the the principle too. Okay, so definition, more precisely. Well, it's actually not more precisely, but it's more clearly written. Definition, let H and G be Hilbert spaces. And of course, there's an addition S multiplication on H, there is another one on G, there is an inner product on H, there's another inner product on G. No, I don't need to write this all down. Let H and G be Hilbert spaces. Then any U from the set of bounded maps between these two Banach spaces. You know, bounded map means you consider them as Banach spaces, which they are, right? So nevertheless, this time not as a thinking, but as an exclamation, right? Bounded, right? Bounded linear. I didn't want to cross it out. I wanted to underscore it, okay. Bounded linear, right? Then any bounded linear map U preserving the inner product, what that is, i.e. U psi, U phi equals psi phi. Obviously, this is the inner product on G, this is the inner product on H, and this must be true for all. Psi phi in H is called any bijection. But that's any bijection is called a unitary map. Remark. Obviously, if such U exists for any two, or for given H and G, these two Hilbert spaces cannot be structurally distinguished from each other by using only plus S multiplication and the inner product. Of course, you could now add further structure to one of these spaces, right? Even further structure, and then you could distinguish them. So you could have a vector space and another vector space that are isomorphic. Okay, I'm still writing. So you could have two vector spaces that are isomorphic to each other at the level of vector spaces, but then you equip one with one inner product and the other one with another inner product such that they're not unitarily equivalent. So adding an inner product, depending on how you choose it, may make the two not unitarily equivalent. Okay? So, but if you only look at, so the same here, you could add yet another structure and then you can distinguish them again. But looking through the glasses of Hilbert space theory, they're not distinguishable. Second remark, by the polarization formula, it suffices to check whether a bounded U preserves the norm. Well, I say the norm. Well, preserves the norm on this, preserves the norms, one should rather say, because there are two norms in the game. So you need to check whether U psi, the norm on G, is the norm of psi on H. Right? I mean, that's simpler. Here you need to deal with for all psi phi in H, and here you only need to check for all psi in H. Because by polarization, because the norm can be constructed from the inner product, but then conversely from the norm you can reconstruct the inner product, that suffices to show. One should add here, obviously, if such U exists for H and G, one should say then H and G are called unitarily equivalent. Unitarily equivalent. That was the notion I needed to define, right? So two spaces are called unitarily equivalent if there is at least one, and then usually many, unitary map between them. And the importance is anything we're going to prove, we can only hope to prove up to unitary equivalence. Because at the level of the structure, unitarily equivalent spaces cannot be distinguished. They may be written down in a different way, but really for all its worth, for all the structure we have, they are the same spaces. So that brings us to the final section. It's not even a lie, it's the final section. 5, unitary equivalence of all infinite dimensional separable, that's the key word here, separable Hilbert spaces. I think I wrote down the theorem before, right? Any Hilbert space, so remember the theorem, any Hilbert space is unitarily equivalent. And sometimes one writes between the spaces then this symbol. And it should have here the symbol with the subscript Hilbert as Hilbert spaces, not as vector spaces, but even as Hilbert spaces. They're unitarily equivalent. That's the mathematical symbol. That's what we say. Unitarily equivalent to L2 with the inner product on L2 that we defined, okay? So please appreciate what an important result this is. Because, I mean, a separable Hilbert space with all these conditions and on. And the question is, how rich is this structure? How many of these things are there? Well, up to unitary equivalence, seen through the glasses of the theory and not more structure, it's only one type. It's a classification, right? Remark, this is, of course, a rather strong, well, in a sense, it's the strongest, right? This is, of course, the strongest possible classification result imaginable? No, the result could have been there are 7 types of Hilbert space, infinite dimensional separable Hilbert space, or there is an integer family of infinite dimensional separable Hilbert spaces. Okay, you name it. It could be terrible. It could be non-classifiable. Like the question is, how many different topologies are there? Well, we don't have the slightest idea how many different topologies there exist. There's no classification of topologies, right? But this is the strongest possible classification. There's only one class. Okay, done. Right? It's not a big classification theory, but it's a very strong classification result. Okay. So if you found a Hilbert space that underlies your quantum system, you don't need to wonder whether there could be another one that could underlie the system. Okay. And essentially, it's always L2 of n for any quantum system. However, in order to deal with it, it's clever to bring it in, to write down different representations of it, right? They can come in different forms, but structurally, they're all the same, okay? That's really good. Okay, so that's the theorem. So proof. What do we need to show? We need to show that there exists a bounded linear map U. Well, let's write it down immediately. U that takes you from the Hilbert space into this L2 space, into this small L2. There's also a capital L2, that's the Lebesgue square integrable functions. That's, well, I can't say it's something different because that will turn out to be a separable Hilbert space, infinite dimensional Hilbert space. So it is like the small L2 of n, okay? But that's another topic. So it exists a bounded linear map H from L2 to n that is unitary. That is unitary. Well, unitary already includes this, right? So, yeah, well, such that u psi equals psi, the psi on H, but the u psi on L2. Well, that's what we need to show. Let's directly construct this map, or explicitly construct this map. So we reconstruct it like u from H to L2 of n, an element psi in H. Well, I make a suggestion for how this map should look like. I need to take an element here, and I need to make it an element into here. What are the elements of L2 of n? Are complex sequences. One element is a complex sequence. This here, what can I do? Well, I choose an orthonormal basis. Choose some orthonormal, Schauder, what else, basis of H. Why can I do this? Why can I choose an orthonormal basis of H? Yes, because we look at a separable Hilbert space. So I should emphasize here again separable. But since from now on we only look at separable, right? I will not always mention it. Exactly. Therefore, I can. So I choose one, and I construct these objects, En, comma psi. So I take a psi, I take the En, comma psi, and I make this into a sequence, because for any n in n, I have a number, a complex number. This is clearly a sequence in the complex numbers. Hence, it's an element, right? So this thing is a subset of the complex numbers. Well, it's a sequence. Hang on a second. Yeah, and as a sequence, it's an element of L2 of n. Well, the question is this really true? It needs to be a square summable sequence. In fact, this sequence, I need to look at the square summability. 1 to infinity, En, comma psi, absolute value squared. okay, is finite. How do we know this is finite?
I would look at the definition and use the auto-morphology.
Normality, yes.
Alright, sorry. And so you get out of the infinite sum just the finite, one finite number of pi I.
Yeah, that's how it goes. That's right.
And that could be
Hang on a second. Schuller basis orthonormal. Yes. Did I emphasize? Yes. So one has that the psi can be written, because we have a Schuller basis, it can be written as En comma psi En. Right? This is easy to check. You have to just deal with the limit and pull it out and pull it in wherever you need. And one has that the psi can be represented like this. So the expansion coefficients we were talking about before, for an orthonormal basis, they are given like that. And then you can check that because the norm of psi on H is certainly finite, it follows that U of psi is square summable. Okay? So while that just says the map does what is claimed what it does. And well, and then you need to check a number of things. Yeah, you can check that another map, which I call innocently U inverse, but it's just a name, another map that goes from L to N into the Hilbert space. How is this now going? Well, I need to start with some sequence, AN, in here that's square summable, and I map it to an element in H, namely the sum n equals 1 to infinity of AN EN. That's the same ON basis, same ON basis E1 to, well, same ON basis E we had before. And again, one can show that this converges because this is square summable and so on. And one can then show that U inverse U acting on a psi. Well, let's plug it in for fun. This is U inverse does this, so it takes n equals 1 to infinity En, but it plugs in the sequence that comes from U psi. But the sequence that comes from U psi is the En psi. We know this is psi. So that means U inverse U psi is indeed psi. That is, U inverse U is indeed the identity on H, right? And thus, U inverse is the inverse. You can also check that U, well, you can also check that U inverse is the identity on L2, okay? And this is, of course, if I write it like this, what is in between here? It's a multiplication, right? No, what is it? It must be composition. I mean, what else? It's maps. So in quantum mechanics, people often talk about the product of operators. They mean the composition, of course. The product comes from the fact that if you have a composition, you go to a basis, and you have a bounded operator, blah, 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 then you can represent this as a matrix multiplication, and they call it the product. But in fact, it's just one map executed after the other. So it's a composition. That's what it really is. Okay? Nevertheless, the term product is in heavy use. But you know better, it's the composition. Okay, so check that, So this is really, this means it's a bijection indeed, okay? And we should check the unitarity bit. Well, one could have proven immediately from the definition of what a unitary is that the operator norm of a unitary map is always 1. Well, we can see this as a corollary from what we're now going to write down, because now calculate the operator norm of U. Right? So on what space is this norm acting? On what space is this the norm?
Bounded, in this case, bounded linear operators between U is from H to L2.
Yes, that's right. From H to L2 of n. This is the operator norm on there. And how is it defined? Everyone? Operator norm. Yes?
Over all norms,
F out of H.
Yes. Yeah?
over the norm of UF over the norm of U. Or the norm of F.
Yes, and this here is, of course, on L2 of n, and this is over H, right? So we need to calculate this. Agree? Yes, it's easy. What do we know? Well, we know that U is unitary, so it preserves the norm. That means this is sup f in H of UF is the same as F, because U is unitary. Right? So the result is 1. Yeah. It's a unitary. 1 unit. No, hang on. What did I do here? Okay, I'm sorry. If U is unitary, then this is 1. Okay? We wanted to show it's unitary, right? Because I constructed a map between two spaces, and I wanted to show that it is unitary. This is true if U is unitary, but we don't know yet. Okay, it's true, it's insightful, it's a nice thing to know because it justifies the terminology unitary, but it's besides the point. Okay, so let's continue with what we actually wanted to do. What I actually wanted to do is I wanted to prove what I assumed. I wanted to prove that this guy is this guy, right? So let's calculate. I'm sorry. UF on the L2 of n space. What is that? Well, UF, I need to write down what that is. That is the, or U psi, we always say, U psi. U takes a psi to the sequence En, comma F, right? That was the sequence U takes us to, n in n. And then U psi, En psi. And then of that we take the norm on L2. Well, of course, the norm eats a sequence because it's the norm on a sequence space. But we can calculate the norm. So that's the definition of U, of our U here. And now this is the definition of the norm on L2. It is I take the individual members of that sequence So they're called the En, size. Take the individual members, and I do an absolute square of them. And that is the norm we have here. Right, so that's one thing. Also calculate the norm of psi on the H space. The norm of psi on the H space is certainly, because I can write psi as this guy, is certainly like this. Aha, and now I need to work. How did I do this? Okay, so the point, of course, is this sum here, right? So I take here the limit of n to infinity of, no, I take it inside, that's the point. So I have the norm, I take the limit n to infinity of the partial sums. Well, that's no secret, that's just the definition of the series, right? Agree? Nothing happened. Well, capital N here. Now, I wish to pull out the limit from here. Why can I do that? Yes, because the norm is continuous. We had this before. Norm is continuous with respect to the limits in this space, blah, blah, blah. So that the whole thing, so equals, limit is outside, n to infinity of, now inside I have only finite sums, En, psi, En. And now there is a sum of vectors and there is a norm. What do I know? It's a finite sum of vectors. Well, that means I have the triangle inequality. I have it for two vectors, then I have it for any finite number of vectors, the triangular inequality. This is less or equal than lim n to infinity sum n equals 1 to n over the individual norms. Agree? That's the triangular inequality. Pardon me? Yeah, but then I have a less or equal to. I'm a bit puzzled. So you say the equality is assumed. It's Pythagoras, actually. It's if we had squares, it would be Pythagoras. Is that right? So Pythagoras is a plus b squared is a squared plus b squared. Isn't that Pythagoras? If and only if a and b are orthogonal. And you can, of course, extend that. So I withdraw. It's an equal sign, and this is Pythagoras. That does that. If I put a square. Agree? But then I need the square. You look puzzled. Agree or not agree? Square, square, square. Yeah, square is also continuous. I can pull the limb out of the square. I think this is right. This is Pythagoras.
Wouldn't we need the square in the upper left corner then as well?
In the upper left, where here? Well, later. I mean, this is one. This is where I calculate one thing, and now I calculate another thing. And you'll see. I wouldn't have needed this first line. I'm sorry. Okay, so just it's true. And then I say also calculate. So I start here with psi squared. Do we agree on all the steps? This
wouldn't be a norm, would it? If you wrote it down like that, because if you
here?
no, at 1.
Okay, forget 1.
Yeah, because if you multiply in the psi with some lambda, then you would get lambda squared out. So
No, here you get a lambda, you get an absolute value of lambda out if you put a lambda here.
But not on the right side, do you? If you just put a lambda in front of the psi, and then you get it squared.
Ah, okay, now I see what, yeah. Well, forget the first line. I wanted to go about this differently. Let's calculate only what I'm calculating down here, okay? So do we agree on these steps? Any supporters? Okay, fine. We have this. Well, and now I pull out of this norm, well, of the squared norm, so this is lim n to infinity, sum n equals 1 to n. Out of this norm, under the sum, I pull out absolute value of en comma psi squared, because the square around, and then there is the norm of en squared, but that's obviously 1. Okay? So this is the limit n to infinity of, this is the sequence, the series n equals 1 to infinity of the absolute value of en comma psi squared. But this is the norm in the L2 space of the u acting on the psi squared. Aha. Ah. The an squared, the u psi squared. Of course. Now I understand the remark. So in the beginning we defined a comma b to be this ai, bi, this one barred, and so on. And then of course, if I now define the a comma a, it's the absolute value a squared, but that's of course not the norm, it's the square root, it's the square of the norm. And that is what you wanted to tell me. Thank you very much. Now I understand. Good. Okay, fine. We use it here, and that's this. So what did we show? We showed that indeed the u preserves the norm. That's it. And that's what we wanted to show. So there exists a unitary map. We explicitly constructed it. And that's it.